think it's time to start. Good afternoon, and we have an exam this Thursday, and I posed the sample exam, and I changed some kind of the section which will be covered on the exam 2. So I included section 11.1 and 11.2, which will be done today and possibly maybe tomorrow, maybe like a 20 or 30 minutes more. But anyway, let's try to finish that. And after that, we'll go over the sample exam tomorrow. And I post that, revise the sample exam, including the chapter 11. And we'll go over that and we'll take the exam on Thursday. Alright, so chapter 11 is about the probability, and we finished the chapter 8 yesterday. And, well, some of them are somewhat like fun, and you may enjoy that. But some of them need some, like the theory and the knowledge. But anyway, let's start.
No review today?
No,
okay.
Because we finished the chapter 8.
Wait, so the chapter we're doing now is for the next unit?
No, that is also on the exam 2. Yeah, I finished the chapter 8 yesterday. So.
Okay.
And this chapter 11.1, section 11.1 and 11.2 will be also on the exam 2.
Okay. All right. And then tomorrow we're going over mock exam?
Yes, right.
Okay.
Yeah.
After we finish 11.
All right.
So the basic concept of the probability is the study of the probability is concerned with the random phenomenon, even though, well, I forgot to bring the dice and the coin. I think I have coin. Yeah, I think I can do it. Even though we cannot be certain whether a given result will occur, we often can obtain a good measure of its likelihood or probability. Any observation or measurement of a random phenomenon is an experiment, and the possible result of the experiment are outcomes, and the set of all possible outcomes is the sample space. The wording looks somewhat like a vague, but well, if I give you some kind of example, then it will be much more clear later on. A subset of sample space is an event. The outcomes that belong to the event are the favorable outcomes or the success. So, just imagine that if we have a coin. Do you have a coin, by the way? I forgot to bring that. Yeah, any coin is okay. So, if we toss this coin just once, what is the outcome? Well, we may either get a head. Well, you can see I don't know whether you can see that, but if you see some kind of the face, that's the head. And if you do not see that, that's the tail. If we toss the coin just once, then we may either get a head or the tail, right? That is the outcome, basically. And the head or the tail, also that is also the event. The head or tail is, if we combine all of them, head or tail, that is a whole space. That is a sample space. Now, if we toss just one coin, then we get either head or tail. But if we have two coins and toss the coins at the same time, then the two of them may have the same head and head, or head, tail, tail, head, and tail, tail, right? That is the whole thing is the 4 possible cases or 4 possible outcomes. That is the event. Each of them is an event, but the whole space is a sample space. And if we toss the dice, like the 6-sided dice, just regular, the typical size dice, then we get a 6 outcome, right? I think you play the dice, right? The rolling the dice, right? That's the probability. And we are going to compute what is a favorable outcome. Let's say that we are going to get just head only after tossing just one coin, then that head is our favorable outcome. But the tail is unfavorable, obviously. And if we roll the dice and, well, if you what is, I never been to the casino, but if you roll the dice, two of them, what is a typical, the thing, if you're gonna win the game, or
Oh, 7.
7,
4,
7. Yeah, if the sum is a 7, then you win the game, right? So if you toss the dice and if the sum of those two is a 7, then what is the favorable outcome is a 7, then what is the probability to win the game? So we want to compute those things. And if you, I think you may play some poker game, right? Possibly, maybe some, not all of you. And we'll discuss the poker game here. And what is like a favorable outcome to get a 4 card or like a flush or the straight, etc. So we'll discuss that. Thank you.
So an event would, like if I'm talking about this coin,
Yeah.
The tail and head are each events,
Yeah, each of them is event.
and then the the favorable outcome, like with the dice 7 would be.
Yeah, that is a favorable.
Yeah, and so how does that fit in with the event?
That is also event.
Okay.
The 7, getting the 7 is also event. But to get the 7, we get a 1, 6, or like the 2, 5, or 3, 4, etc. Each of them is an event. I think it may be fun, right? Like for today, we may get I think we had a rain in the morning, right? So there is a chance to get a rain or like the sunny day or the rainy day or the cloudy day. There is also like you can see some kind of like the probability, like the percent, like the 50% of the chance of the raining and so on. That is a probability. So if, for example, this is an example, if a single coin is tossed and we want to find the probability that it will land head up. I think we know that. We know the answer. Like, if we toss the coin, then we assume that if it is a fair, it is like the fair coin is that there is nobody treat it like that. How can I say? Like a fake coin. Sometimes they make a fake coin, right? So they may like the head appear more than the tail. It is possible, but anyway, let's assume that it is a fair coin. Then the probability of getting the head is 1/2, right? If we toss the 2 times, then L is, well, if this is a theory, then we get a 1 head and 1 tail in a theory, right? So there is like the theory, and which is like the theoretical probability. So for this one, this is like the theoretical probability. For the theoretical probability, well, we don't really toss the coin. We don't do any like the experiment. So we use our knowledge based on the given condition. So the solution is we assume that head and tails are equally likely, or simply say that it is a fair coin. We always assume that it is a fair coin. So if we toss the coin twice, then one time we get a head and another time we get a tail. We can do the experiment, obviously. And then the experiment means we toss the coin. Single pair coin. Then, I think from this point is important, the sample space. For the sample space, we use the letter symbol S for the sample space. the sample space is either head or tail. So we use head for H and tail for T. That is a sample space. Now event, we want to get the head, right? Each of them, head and the tail, each of them are like the event, but our favorable event is head, right? So,
And so you say it's your favorable event because that's what you had called?
yeah, that's what we want.
Yeah.
Because that is what they asking.
But not all probability has a favorable event. I mean, sometimes it's
Yeah,
just...
well, it is not. It is
Right,
not.
right.
Sure, obviously. So, event is, in our case, we want to get the head. So, event use a letter E, where the favorable event is a letter E, and that is an event is H for the head. That's what we want. And then the probability of head is, so the event where the favorable outcome is just one, well, which is head, just one element. And then the total space where the sample space is 2 outcome or the 2 event total. So that is a probability of getting head is 1 out of 2. So 1 out of 2 possible or the possibility. So the probability of head is 1 over 2. Simply, we say that this is a probability P of event H is 1/2, or the probability of event, our event, if we say the event is H, set the element of H, and this is also 1/2. So, in this, we'll always use the sample space. If I say that just S, and that represents the sample space or the whole space. All possible combination or all possible event or the outcome. And the event, if I say the event E, then that means that is a favorable outcome. So in our case, like we want to find the probability that it will land head up. So the head is our favorable outcome. So the event is the head H. And then, if I say the P of H or the P of E, that means the probability of event. Our event is something. And this probability P is always between 0 or 1. The probability of the 0 is, it never happened. It never happened in the life. So let's assume that we have a dice, and we toss that, and the dice has 1 to 6. From 1, 2, 3, 4, 5, 6. And then we are get the event, which it landed on the 7. It never happened, right? So the probability of the 7 is 0. It never happened. And the probability of 1, it always may happen what is the event? If we toss the dice, what is the event? The number is between 1 and 6. It always happens between 1 and 6, right? So that probability is always 1. But in between, the probability is always in between 0 and 1. So this is a theory. We never toss the coin. We know that when you toss the coin, we're going to either head or tail. But if we do some experiment, well, for some time, there is no good theory, or we cannot make a theory. So let's assume that if a cup is tossed, just plastic cup, or a styrofoam cup, a cup, if a cup is tossed, and we want to find the probability that it will land on its top. I think it may be most of the time it never land on the top. or land on the bottom. It's just on the side, right? So you just have to try. You just need to try that. So need to find the probability of if we toast a cup, and what is the outcome. So we actually count this, and this is called as empirical. Empirical probability, because there is no theory. There is no exact probability of getting the head or getting the bottom. It totally depends on the cup itself, right? Or there's some kind of the environment itself. So we actually have to do this.
Is that because the answer is almost infinitive? I mean, you can't determine with the flipping of a cup. There's so many variables.
Yeah, there are so many variables.
So that's kind of what makes this possible
right.
here.
That is also depend on the cup itself, the shape of the cup, or if you do the inside of in the classroom or the outside.
Yeah,
so
yeah.
that depends on the case. So a cup will land on its side. Most of the case, its side much more often than on its top or its bottom. So to get an idea, we actually have to do that. I didn't bring the cup. But.
So would you say a sample set is the results of your experiments?
The
Or
sample
is it
space, you mean the sample space?
Yeah, or is it all the potential outcome?
All of them.
Yeah, so regardless of whether I did any experiments, since I know flipping a cup, there's just no real one answer. It's empirical.
If you toast the cup, there are only 3 possible outcomes. Either on the top, bottom, or on the side. That is the sample space.
Right.
But each of them has different probability. Probability of on the top is different from the probability on the bottom or on the side. They have just a different probability, but only 3 outcomes are possible. Right? Isn't it?
Well, I mean, theoretically, there's more. It could land kind of up against the table and sit on the top or edge. I mean,
in a theory, we don't.
So the space is not all the potential answers.
It'll be 1/3. How that work?
No, that is not just 1/3. So the reason is if you toast the coin, it always either land on the top or on head or tail.
Yeah.
There is no it land on the side. You cannot. Well, maybe, but you don't expect that, right?
No, right.
So we don't count that. But if you toast a cup, just a plastic cup or the paper cup, then there are 3 possible ways.
Okay.
Either on the bottom, or on the top, or on the side. Most of the case, on the side.
Yeah.
Right? So it is not just 1/3, because on the side you expect more. It lands on the side more times than on the bottom or on the top. So the probability of getting the top is not the 1/3. Although the sample space itself is 3 possible cases.
It just seems weird because the probability is based on my understanding of the potential outcome. 3 sides of the cup, top, bottom, or side, right?
Yep.
But when you're doing probability on things that you don't have a good understanding of,
then you have to do the
experiments,
Yeah,
and then you get
you
a
have to do
set
these.
of information, and
That's
that
right.
becomes, right?
So to get an idea, we actually have to perform, but I forgot to bring that. So there is no exact answer for this. It totally depends on the situation.
I got you.
Yeah. Experiment and toasting such a cup, well, let's assume that we toss the cup just once. Do we expect getting some like the good result or the good like the probability? No. The answer is no, right? So we have to toss a cup many times, 10 times maybe good, or the 50 times or 100 times. If we toss more and more, we get a more accurate measure of the cup, right? That's what we expect. So typically for the experiment, this kind of like the experiment or the empirical probability, the higher or the larger, like the trier, is usually better. But we cannot do infinitely many times. So typically we do like the 50 times or 100 times only. So there is no like the exact answer for this empirical probability. So let's say that we only toast a cup 50 times. So assume that it landed on its side. And most of them will be like on the side, obviously, 44 times. And on its top, 5 times. And on its bottom, 1 time. Typically the cup, the top is slightly larger, right, than the bottom. So we expect more time on the top than the bottom. These numbers are not exact. If you do again, they will change, obviously. You may get a different answer. Then, based on this, if you want to get the probability of the top, is about 5 out of 50, which is 1 over 10. Don't worry, I'm not going to ask you, do this on your exam. No, there is no way. Because there is no exact answer. So I cannot do that. We cannot do that. But anyway, this is like a probability. So for the probability, there are 2 probabilities. One is the theoretical. It is exact. It always assumes that it is fair. It always either one or another, etc. And then also, we may get an empirical probability. For the tossing a coin, the exact probability of getting head is 1/2. But if we do the experiment, if we toss the coin 50 times, we may not get like a 1/2. We may get like let's say 24 out of 50 for the head. It is possible, or the 23 out of 50, right? So there are 2 probabilities. So theoretical probability and then empirical probability. So for the theoretical, which is like the example 1, and the empirical is like the example 2. For the theoretical probability, if all outcomes in a sample space S are equally likely, the point is equally likely, and event E is an event within that sample space, then the theoretical probability of event E is given by the following. I think you may know the answer. So probability of event E is, we have a set, we have like element on the set E, right? And then we also have an element in a set S, like this. The sample space S, we have 2 elements, and the event E, we have 1 element. And we count how many elements are there for each set. And then we get a probability is 1 out of 2 means we only have 1 element in an event E and the 2 elements in an event like the sample space S. So we count how many are there. So the probability of E event is a number of favorable outcome over the total number of outcomes. So that is simply we count the how many elements in the set E and how many elements in the set S. So this N, this is the letter N, is a number of elements in such and such. So we count the number of elements in the set E over the number of elements in the set S. That is a theoretical probability. So if we toss the dice just one time, and if you want to get just one, land on one on the top, then the number of the favorable outcome is just E is equal to 1, and the total outcome S is 1, 2, 3, 4, 5, 6. So the probability of getting 1 is 1 out of 6. And if we toss like the dice, and if you want to get an even number, the even number is 2, 4, 6. That's the even number. So event E has a 2, 4, 6. There are 3 elements, and the sample space is 6 elements in it. So the probability of even number is 3 out of 6, which is 1/2. Does it make sense? And empirical probability formula is an event E is an event that may happen when an experiment is performed. Then an empirical probability of event E is given by the following formula. It is almost the same as before, but the word is slightly different. So the probability of event E is number of times that the event E occurred over the total number of experiments. So in a previous example, we tossed a cup 50 times. Then the denominator total number of experiments is 50. If we toss a cup 100 times, then the denominator is 100. And the number of times event E occurred is, if you want to get a top, like the previous example, it occurred 5 times only. So the probability of on the top is 5 out of 50. If you want to get a probability of land on its bottom, then the probability of the bottom, the P of bottom is 1 over 50. If you want to get the side, the probability of the P of side is 44 over 50. That is a probability. Does it make sense? Most of the time, I do not ask like the empirical, this kind of a question on the exam, because you have to toast that. So you assume that that is always like on the theory, based on the theory, and based on the fair coin and etc.
Can you go back to the slide for this one?
Which one? This one?
Yeah.
This one?
It was ahead. No. It said theoretical and empirical probability formulas.
This one?
Yeah.
Yeah.
Okay, I got it.
Okay?
So when would you use those two? I mean, what determines?
You mean the empirical or what?
Yeah, between those
Empirical?
two different versions of probability, it seems like empirical, it would only be if I were doing experiments and I'm trying to figure out something based on my results.
That's right.
And the other one, maybe because I already know the possible
Yeah,
results and
you
I'm just
know.
estimating
Yeah,
it.
That's right. Because for the probability of getting pad is, we assume that it is really fair and they are equally likely in a theory, right? In theory, equally likely, so we can get the theoretical probability. But like the cup, it totally depends on the cup, or the situation, or the environment. So you have to do that by yourself. If you want to get like the empirical probability of getting a pad by tossing a coin, then you can do that. We'll actually do that in our next. Where is that? Yeah. Oh, yeah. If we go like slightly further, there is like an experiment, the actual experiment. So we maybe toss the coin. Okay, let's discuss the next example. And Kathy wants to have exactly two daughters. Never happened in the real life. So assuming that boy and girl babies are equally likely, and find a probability of success if A, she has a total of 2 children, and B, she has a total of 3 children. So the assumption is equally likely. The boy and the girls are equally likely. In the real life, it is not equally likely. If you go to like Google, if you Google that, what is the probability of like the boy versus girl? The boy has a more chance. So boy versus girl is a 51 to 49. So there are more boys than girls. Why is that? The reason is usually a boy goes to the war, so they die. So there is more chance to lose the boy than a girl. And then it is also based on that is also based on some kind of evolution. And then also maybe based on the gene expression. I don't know. You may do the experiment, or you may search that. Anyway, but no one for sure because there is no the great theory yet. So anyway, let's look at that. So we need exactly two daughters. And the sample space for the A so if there are 2 children, then the sample space is either can be a boy, girl, boy, or the girl, right? So there are 4 possible cases. So it can be the 2 girls and girl, boy, girl, boy, and boy. If they are equally likely. And the event E, what is the event E in this case? What do we want? We want to get exactly 2 daughters. So the event or the favored event is G, girl and girl. And then the probability of event E, where the 2 girls is number of event over the number of sample space, which is 1 over 4. That's the possibility. That's the probability.
So it's interesting that the event results were not based independently. I mean, you're looking for the event actually being 2 events at one time together. 2 girls back to back, 2 events, and
Yeah,
equals
that's
1
right.
event.
Yeah. But on the next one, it doesn't need to be because there are 3 children. So there is order in the children, right? Obviously. This girl means, well, the first one is also girl and the second one is also girl. Girl boy means the first, maybe we can reverse that, but we assume that the first child is a girl and the second child is a boy. And this is different. They are different, boy and girl. Boy and girl, boy, they are different because there is order. And let's discuss the second case. Now there are 3 children, so the sample space S. For the 3 children, there are more possible ways, right? So it can be all girl, or the next one is 1 boy. So, but the 1 boy can be anywhere. So girl, boy, G, B, G, B, G, G for the 1 boy. The next one is the 2 boys, right? So G, B, 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 G, B. What is that? B, B, G. The last one is all boys. So B, B, B. That's the sample space. How many?
8.
8. Yeah, 8 possible ways.
So since it's a 50-50 chance, could you just do like 1/2 times 1/2 times 1/2?
That is a 3 girls. Or the 3
But if
boys.
It's a 50-50 chance.
Yeah, we will discuss that. Yeah, 50 for the 50-50 chance. But for the 1/2 and 1/2, we also have to count how many possible combination of boy and the girl. So it is not just a 1/2, 1/2, and 1/2. It is slightly different. Yeah, it is actually an easy mistake. Easy to make a mistake. Those kind of a mistake because it looks like just 2 boys or the 2 girls out of 3 children is 1/2, 1/2. But it is not. Yeah, better to like count the exact number. That's the best way. And then our event E, we want to get only 2 daughters or the 2 girls, which is not this one, which is this one. 2 girls, 2 girls, 2 girls. Those 3, right? So G, G, B, G, B, G, B, G, G. So the probability of event E, or the exactly 2 daughters, is 3 out of 8. That's the probability.
And the $3 scenario just doesn't apply because it's not exactly 2.
Yep, because it asks exactly the 2. Exactly 2 only. Now we can make a following example. What is the probability of getting the same genders for the 3 children? All same gender. What is that?
2 out of 8.
Yeah, 2 out of 8. All girls or all boys. So that's the same genders, which is a 2 out of 8. That's the probability. Does it make sense? Yeah.
Yeah.
So this is about the 5-card poker. So I know some of you may not know what is like a poker card or something like that. Yeah. So this is the card. I think most of you already seen this or played with this card before when you're young, right? So anyway, for the card, when I say that the poker card, And then there are 4 types. The first one is like a club. Second one is a spade. Third one is a heart. And the fourth one is a diamond, right? And A, this A stands for, we only have just one. That is, A is the same as 1. And the 2 diamond and 3 diamond, etc. Well, I think that should have color. I don't know whether you can see the color, but the first 2 are black, and the second 2, third and the fourth are like the red. And we also have a face from 1 to 10. There are diamond, but for the last 3, we have a J, Q, K. We have a face card. So when I say the face card, then I always refer to J, Q, K. That's the face card. When I refer to the ace, we say that this is ace. So there are 4 possible aces. So if you're good at this, like playing poker games, then maybe you understand better. So let's do the following. Now we're going to find the probability of being dealt each of the following hands in 5-card poker. So 5-card poker means we have a 5, we choose a 5 out of this 52 possible cards. So one of the name is a full house. The full house, this is like a 5 card. The full house is a 3 of 1 denomination and the 2 of others. So that means we have a 5 card, but on that 5 card, we have a 3 card are the same shape. And the 2 is the same shape and the same, like the number, isn't it?
Yeah.
That should be the same number, sorry. That should be the same number. So the 3 cards are the same number, like the 2, 2, 2. And the other 2 are a different number, like the 4, 4. That is a full house. And then the part B is a royal flush, which is a 5 highest card, ace, king, queen, jack, then of a single suit, which is like if we have a and this, that means for the diamond we have a from the 10, J, Q, K, and A. So that is what this refers. Where is that? Yeah, over there. Yeah. That is ace, king, queen, jack, 10. That's a 10, not 10. Sorry, that's the typo. 10. That is a royal flush, and there are 4 possible royal flush, as you know. So anyway, if you want to compute the probability, so let's try to compute that. I'm not going to do that, but for the card we have a royal flush. How many possible ways? So if we go back here,
There's 4 sets.
we have a 4 set, right? For this, we get a 1. So ace, this diamond A, 10, J, K, J, Q, K. And for this heart, we also have 1. And for this club, we also have that club, we have 1. And for this spade, we have 1. So there are 4 possible ways to get a royal flush. So we have a 4. There are 4 possible ways. And the next highest length is, do you know that? What is the next one?
What?
You don't know the next, like the highest ranking? You don't play the poker. You're a good student.
Yeah.
I don't play.
4 of a kind?
So there is a straight flush.
Yeah.
The straight flush is, we only have for the 5, we have like on the same set, should be on the same set, but like continuous number, like the 2, 3, 4, 5, 6. Those kind of things. That is like the straight and flush. That is the same shape, and then like a continuous number. That's the straight flush. And there are many ways, because it is not just 2, 3, 4, 5, 6. It also can be like 7, 8, 9, 10, J, etc. So there are many, really many possible ways. So, but not that many. There are 36 possible ways. Something like that. Right? And the next one is 4 of a kind. These are like the 4 card.
Yeah.
Yeah.
The same.
So the 4 card is all like the based on the just column. So A, or the 2, 2, 2, 2, 3, 3, 3, 3. Those are like the 4 card. But the other card can be just any number, right? It can be any number. So there are more, not just like the 13. If we only count like the 4 card, there are 13 possible ways, but the other 1 card can be any of them. So there are more, which is 624 possible ways, which is a lot. And the full house is 3,744. So the full house is the same number for the 3 of them, so like the 2, 2, 2, but the 2 of them are different numbers, like the 4, 4. But have to be like the same numbers. So only 2 possible numbers out of what?
I'm sorry, you said 4 of a kind. There was how many possible? Isn't there 13 possible 4 of a kinds?
So we have a 5 card. The last 1 card can be any number.
Right.
So it can be more than just a 13.
But even though you don't really care what the last number is,
We
it's
don't
still
care
part
that.
of it?
So we don't care that, but we have to count all possible ways to get the 4 card. Does it make sense?
Yeah, I was just thinking you were only putting your favorable outcome number there, not the every
No,
possible.
but let's say that we only got like a 4 card. 4 card is a 2, 2, 2, 2, but the last 1 card can be any of these remaining.
Yeah.
So, how many? So 52 minus 4, 48. So this 13 times 48 is a 4 card, which is 624. Does it make sense?
Okay.
So, well, there are more. So the flush, well, the reason is that you may need this, not for your exam. I'm not going to ask you this. Like, what is the probability of the royal flush, etc., because there are so many ways, but it may be needed for your homework. So 5,108, and the straight is a lot more, 10,200, and the 3 a kind is a 54912, and 2 pairs. 2 pairs is same card like a 2, 2, 3, 3. So that's the 2 pair. And the last 1 card can be just any number. So 1, 2, 3, 5, 5, 2, 1 pair. 1, 0, 8, 9, 8, 2, 4, 0. And no pair. There are a lot more. And then the total is, let's write down the total here. Total is 2598960. That's the total. Wow, that's a lot,
Yeah.
right?
Two and
It
a half
is a
million?
2 million possible, more than 2.5 million, 2.6 million ways for this kind of card game. It's almost impossible to win the game. Looks like that. Anyway, that's that. So, if you want to get a probability of getting the royal flush, so that means you almost never see it during your life, although you play that all the time, because the probability is so low, or over almost like the 2.6 million. That is a probability. It is almost like impossible. So you can get the probability of the straight flush, 36 out of this number, and 4 of a kind or 4 card is 624 out of this number, etc. So anyway, based on this, we can get a probability of a full house. So, which is a probability of a full house is 3,744 out of 200, 2 million, that's hard to count, 2598960, which is about 0.00144058. It is somewhat like a really rare probability, but the probability of royal flush is much more rare.
Where is the 3744 from?
Oh, that is this full house. Yeah, that number. Don't worry, I'm not expecting you to remember this. Because I don't remember that. So royal flush is, we only have a 4, so 4 out of 2598960, which is about really rare, 0.000000154. It's like winning on a rotary, right? Almost the same as that probably.
This time you did a decimal answer. Is that what would be normal, the fraction or the decimal?
It doesn't matter.
Okay.
Yeah. Any other question?
And you just got that decimal by dividing the top number by the bottom number.
Yeah, that's right.
Okay.
Yeah. Okay, that is here. I count that. So let's do the following example. We don't need to count those kind of things. So U.S. population at the end of 2006 included 148.2 million males and 152.8 million females. So there are more females, right? As I said, there are more chance to survive or like having a baby or anyway, that kind of thing. So if a person were selected randomly from the population in that year, what is a probability that the person would be a male or maybe a female? So the probability of a male is number of males over the total population, which is 142.8. Sorry, 180. Yeah, 48.2 million over 148.2 plus 152.8. So both of them are million, right? So the units are cancelled out. and this is about 0.492. You can say that this is like an empirical probability because there is no like the theoretical probability for this. This is based on the empirical or the experiment. The theory should be just exactly 1/2 or 0.5. But there are so many variables in the light, so. Law of large numbers, as an experiment is repeated more and more times, the proportion of an outcome favorable to any particular event will tend to come closer and closer to the theoretical probability of that event. So, as I said, like toss a coin, if we toss a coin like 2 times, maybe we make it just head and head, right? For 2 of them. It is possible, but if we toss a coin more and more, like 50 times or 100 times, then the probability of getting head is almost the same as probability of getting tail, right? So we know that. That is a large law of large numbers. So we have to do a lot of experiment, or we have to get a lot of sample to get a better approximation to the theoretical value. So let's discuss this before the break. So a fair coin was tossed 35 times. Let's say that we perform some experiment and producing the following sequence of outcomes. So tail, T means the tail and head means the H means head. So T, T, H, 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 that means the first time tail, second time tail, third one is the head, fourth one is the head, and fifth one is the head. So we cut it as like the 5 because we want to count that. So let's say that we have those kind of the sequence and we want to calculate the ratio of head to total tosses after the first toss and the second toss, and then we continue that up to all 35 tosses and plot these ratio on a graph. So for the first trial, we want to get the head. We want to get the head. So for the first one, there is no head, right? So the probability of getting head is 0 out of 1. For the second, still for the tail, so there is no head, so still 0 out of 2. Now at the third time, we got a head. So we got a head, 1 head out of 3 trial, and then we have 2 head out of 4 trial, we have 3 head out of 5 trial, we have 3 head out of 6 trial, I'm going up to that, and then we have 3 head, 7, 3 head, 8, and then 4 head, 9, 5 head out of 10, etc. So these are the probabilities, right? Now if we plot this, this is a number of tosses, and this is a ratio. And then for the first time we get a 0. 0 over 1 is a 0. We also get a 0 for the second time. In the third time we get a 1/3, which is around that. And we have a 1/2, which is here. And then it goes up slightly higher than 1/2. And then 1/2. And it goes down because there is a 3 over 7, and then 3 over 8, it goes down further, and it goes up and goes up. So if we plot that, we got then it may follow very close to this line. You expect that, right? So as we do more and more experiment, the empirical probability is getting closer and closer to the theoretical probability, which is 1/2. That is a law of large number. So if we do more, we get a better estimate or the better probability. Yeah.
Can you help me understand how you're plotting that? So 0, 1 in the bottom left corner of that graph is the first point, and then 0, 2.
Yeah, this is the first point, that, and this is the second point, because the value is a 0, and this is the third point, that is 1/3. And this is the fourth point, which is a 2/4. And this is a fifth point, 3/5. It is slightly above than 0.5. And then this is a 3/6 is 1/2. So
But
settle down again.
What I mean is I'm used to seeing, number, comma, number
Yeah.
for X and Y. And so X,
X is a number of toes.
yeah,
So 1, 2, 3 toes, 4 toes, 5 toes, 6 toes, etc.
right?
And this is a Y value, or the ratio.
And so you're going up 1, then 2, then 3. But then the next one should be exactly 3. All of those should be 3.
This one is this.
Yeah.
And this number is this.
And then 3, 5.
Yeah, 3/5 is higher than.
Yeah, but then the 3, 6 should be straight next to
Yeah,
it.
that is this.
It's
Wow,
below it.
Lord. Yeah,
That's what's throwing me off. That's below the 3, 5. It should be equal to.
What do you mean? Equal.
They're both 3. If the number is
3/6. We have a 6 total outcome. 6 trial. From the 6 trial, we have 3 half. So 3/6 is a probability.
I
That
guess
is a ratio. This is not like the number of hat. We are counting the ratio or the probability.
I get what you're asking. You're trying to look for like a coordinate with parentheses.
Yeah, right. That's what I'm
So like the first one,
Ah, I
0
see.
0/1 is 0, so it's 1, 0.
Yeah, 1,0. The second point is 2,0. Third point is 3, 1/3, and the fourth one is 4, 2/4, and then fifth 5, what is that? Yeah, 3/5, and the 6, etc. So that is the first one is like the number of toes for the X values, and the second one is like the probability. This kind of the probability or the ratio. Is that what you're asking?
Yeah, I'm just saying, though, on the graph itself, 3, 5, and 3, 6, if you're following Y as the 3, it should be exactly across 3. It shouldn't be going like this.
No, that is it depends on. This is we are computing the ratio. This ratio, this value. We are not computing the number of head. We are not counting the number of head. For the number of head, it is always increasing. It never decreases.
he's saying why did the point drop on the y-axis though?
Because of this, 3, 5,
He feel like
and
it should
3,
be
6.
I don't know, bro.
This is
I
larger.
know.
3/5 is larger than 3/6.
Right, so I guess, I'm used to the ordered pair 1, 0, and
Yeah.
that's showing you the location on the graph. And now you're using a fraction, I
Yes.
guess, and the number on the bottom is the number of attempts, and then the fraction is the y
The number of
coordinate.
the bottom number is the number of trial. That's
Right.
But this also represent the numerator over the denominator represent. That is a ratio or that is a number. There is another number. 0/1 is a 0. 0/2 is the 0. 1/3 is a 0.33, etc. That is a number or that is a probability.
Wait, you think it should be like, because it's going up, it's going 1, 2, 3,
Yeah.
but it's going 1, 2, 3. Does that make sense?
The number of tosses.
Wait, can I point it out? I kind
Yeah,
of
yeah,
know what you're
sure.
talking about. You're confused because it's going 1/3, 2/4, 3/5. Are you confused with why this this is a 3 and then this goes down, but that's a 3?
Yeah.
Okay, this, 1, 2, 3, 4, 5, those down here are these points. So this is the 1.
Right.
This is 2, 3, 4, 5, 6. But this is a whole. You can't separate those.
So it's a fraction. You're
Yeah, that is
going
a
up
fraction.
3/5 or 3/6.
Yeah, that is a fraction.
And so how did you figure that out so bad? How'd you put the dot there?
Because 3/6 is 1/2. So you go back down to the 0.5, which is 1/2.
Okay.
But you're on your 6th dot.
Right.
Did that? I don't know if that was.
That makes sense, I guess. And then 3/5. How did you know that was above the 3/6? Seems like an obvious answer, but
Divide it, 3/5 and 3/6.
right. Okay.
Yep.
That value is higher, so it's going to be higher.
Yeah,
on the
this
graph.
3/5 is 0.6, and 3/6 is 0.5.
Right.
So that is higher. That is above. This point is above.
Okay.
Yep. Okay, I think it was a good discussion. Let's take a 5-minute break.
I've actually got a website on how to beat the lotto, howtobeatthelotto.com. And I use a spreadsheet, and I try to use probability to look at past results and find patterns, and then make predictions based on the patterns. Mm-hmm. And so it's a cool website, but I've never really spent much time on it. I put it out there. Some people check it out, but I ain't won the lotto yet.